Hi, welcome to the latest video. This one will deal with de Moivre's theorem. Abraham de Moivre was a French mathematician in the 17th century who found a very neat way of working out powers of z in complex number form. So let's see what this is all about. A complex number, and we usually use the letter z for that, is represented by z equals a plus bi. There we are, where a and b are real numbers and I is the symbol that is used to state that it has the property of I squared equals -1. Now that's counterintuitive, isn't it? I mean, you might have been taught that when you square any number, whether it's positive or negative, that the answer is always positive. But now we have to accept that there is an imaginary number, I, such that when it's squared, we get a negative answer. But let's accept for the moment that property because it will be useful. But before we develop the formula for de Moivre's theorem, let's see where the set of complex numbers fits into our current idea of number systems. At the very basic level, we have our set of natural numbers represented by capital N, and they are really our whole numbers, our counting numbers. And when we extend the natural numbers, we obtain the set of integers represented by capital Z, and we extend the natural numbers by including a 0 and all the negative numbers. So integers are all the positive and negative numbers including 0. And then extending the integers, we have what we call the set of rational numbers represented by Q. And basically rational numbers means any number that can be written or expressed as a fraction. For example, all the fractions by default are rational numbers. What about 2.555 recurring? You'll see that there is a fraction that when converted to a decimal gives you 2.555 recurring. You might like to investigate that. For example, 0.3333 recurring is equivalent to the fraction a third. Okay, let's extend the rational numbers. And when we do, we obtain the set of real numbers represented by R, and the real numbers also include numbers such as pi. You might have come across that when dealing with areas of circles, 3.141 and so on. And E, which is approximately 2.718 going on forever. And the square root of 2, a surd. Surds, such as the square root of 2 and pi and E, are what we call irrational numbers because they can't be written as a fraction. In other words, they are non-recurring decimals. And then finally, which is what we want to do in this video, we want to look at the set of complex numbers represented by C. Okay, let's get down to developing de Moivre's theorem. Let's begin by looking at what we call the complex number plane or the Argand plane, which is very similar to the normal Cartesian plane that you might have been using, where you have your x-axis along the horizontal and your y-axis along the vertical. But in the complex number plane, the horizontal axis is referred to as the real part of our complex number z, and that's what RE stands for. And on the vertical axis, the imaginary axis, we label that as IMZ, imaginary part of Z. And looking at a particular example, let's suppose we have a point on our complex number plane. There it is, represented by Z equals X plus YI. X, of course, is the real part of Z, and that would be down there. And the Y would be the imaginary part of Z, which we can show as there. And a few other properties we can get from that situation. As we said, the horizontal is X, the vertical is Y, And if we use Pythagoras' formula using this right angle triangle, we can work out that the distance from the origin to point Z is the square root of x squared plus y squared, which we represent as the modulus or the absolute value of Z. That's what those two vertical lines represent. There's also another way of representing the complex number on the complex number plane, and that is in polar form. And this is the way we're going to develop de Moivre's theorem. Now, with a bit of simple trigonometry, if we specify the angle to be theta in this right angle triangle, then using properties of trigonometry on the right angle triangle, we can say that the horizontal component, which is this one, is equivalent to the magnitude of Z times the cosine of the angle, and the vertical side of the triangle is the same as the magnitude of Z times the sine of the angle. To work out the angle theta, we know that tan theta is y over x, so the angle theta would be inverse tan or arctan of y over x. Okay, just to summarise that, there's our Cartesian form, there's our polar form. Let's develop that a bit more. We have z equals x plus yi, of course. What we can do is substitute our expressions for x and y in polar form. So we know that x is the same as magnitude of z times cos theta, and of course y is the same as magnitude of z times the sine of theta. So we have our expression for z in terms of angle theta. And we can simplify that a bit more by taking out the magnitude of z as a common factor, like that. And we can abbreviate the expression and write cos theta plus sine theta I as cis theta. And you can see where the letters come from. The C comes from cos, the I is the imaginary component, and S is for sine. So in complex polar form, the number z, the complex number z, can be written as the magnitude of z cis theta. And here's the actual theorem. It states that for complex number z, given by magnitude of z cis theta, then z raised to the power of n, where n is an integer, is equal to the magnitude of z to the power of n times cis of n times theta. We can prove this by induction, which is a common proof. We know the theorem is true when n equals 1, because n equals 1 just means we have what we started with. Let's show that it's true for n equals 2. So there's our z in expanded form. Z squared means z times z, and magnitude of z times magnitude of z is magnitude of z squared. And then we have these two brackets multiplied. We now expand the brackets into those three terms. Notice what we have here at the end, I squared. Now I squared, using our original property that I squared equals negative 1, means I can replace I squared with negative 1, and that gives us negative sine squared theta, which I've put over to here. One of the trigonometric properties is that cos squared theta minus sine squared theta is the same as cos 2 theta. And another trigonometric property states that 2 cos theta sine theta is the same as sine 2 theta. So notice what we have now. We have z squared equals the magnitude of z squared, and of course this part we can abbreviate as cis 2 theta. So we prove that it's true for n equals 2. Now to generalize the proof, that means to show that it's true for all values of n, we assume that it's going to be true for some value k, some integer k, where k is greater than 2, because we've already shown that k equals 1 and k equals 2 is true. So we can write z to the power of k plus 1 is the same as z times z to the power of k, and replacing z and z to the power of k in cis form, this is what we have. And we can do that here because we've assumed that it's true for n equals k. And now magnitude of z times magnitude of z to the power of k is the magnitude of z to the power of k plus 1. and writing each in expanded form, cis theta is the same as cos theta plus sine theta I, and similarly for cis k theta. There it is. We now expand the brackets into its real and imaginary parts, and we obtain this expression. And now we use two more trigonometric identities, and the first one is the one shown here on the left. That means I can replace this bracket by an expression that looks like cos A plus B. There it is. Our A will be theta and our B will be k theta, like that. Similarly, the second trigonometric expression, sine A plus B, I can replace this expression with sine k theta plus theta. And just to make things a little easier to work with, factorising k theta plus theta by taking out a factor of theta, it looks like that, and the same thing over here. Cos theta k plus 1 theta times sine theta k plus 1 theta, we abbreviate as cis k plus 1 theta. That's really the end of our proof, because we've shown that it is true for n equals k plus 1. So if it's true for n equals k plus 1, it must be true for all values of n, because our value of n was arbitrary. It was any value greater than 2. Now this proof is valid for positive values of k, but you can use a similar approach to show that de Moivre's theorem is true for negative integer values. Okay, let's apply the theorem. Now here's an example we could try, but first of all we will work it out without using the theorem. Let's suppose a complex number is z equals 1 plus I, and we want to determine the value of z squared. Z squared is 1 plus I squared. If we expand the brackets, we obtain 1 plus 2i plus I squared. Now I squared we know is the same as negative 1. There it is. Simplifying, 1 minus 1 is 0. So we end up with z squared equals 2i. Now let's see if we can obtain the same answer using de Moivre's theorem. There's the theorem. This just shows you what we're going to use in polar form, of course. So we have z equals 1 plus I, and we want to work out z squared. First thing is to work out the value of the magnitude of z, which is the square root of x squared plus y squared. Our x is 1, and our y is the coefficient of I, which is also 1. So the magnitude of z will be the square root of 2. We now want the angle theta, and we know theta is the inverse tan of y over x. There's our y value, 1, there's our x value. So inverse tan of 1, if you work it out with a calculator, is 45 degrees. So putting that information in our expression for z, we have z equals square root of 2 cis 45 degrees. Now we want z squared. So z squared according to de Moivre's theorem will be the square root of 2 squared cis 2 times 45. And that simplifies. Square root of 2 squared is 2. 2 times 45 degrees is 90 degrees. Now writing that in expanded form, that's what we obtain. Simplifying, cos of 90 degrees is 0 and sine of 90 degrees is 1. So we have 2 times 0 plus 2 times 1 times I, which simplifies to 2i. Same answer as using the expanding of brackets method. Now before we go on to another example, we can use what we refer to as reference triangles to give us exact solutions to some of the questions where the angle involved is going to be either 45 degrees or 30 degrees or 60 degrees. And here's the first one. If we have an isosceles triangle like that, each of the angles here is 45 degrees, and being isosceles, let's say the two sides are 1 and 1, and then the hypotenuse will be, of course, using Pythagoras' formula, the square root of 2. So that means using trigonometric properties, I can write that cos of 45 degrees is 1 over root 2, and similarly for sine of 45 degrees. And also tan of 45 degrees is 1 over 1, which is 1. We can also write the angles in radian form. 45 degrees is the same as pi over 4. So we can write exactly the same expressions using radians. So cos pi on 4 is 1 over root 2 and so on. Similarly, as I mentioned, we can also use 30 degrees and 60 degrees. Now let's say we start with an isosceles triangle. That means each interior angle has to be 60 degrees. And let's suppose the side lengths are each 2 units in length. Here, of course, we have the same situation using radians. If we divide the triangle into 2 equal right-angled triangles, let's say the base of here will be 1, half of 2. The angle here is still 60, but the angle at the top is going to be half of 60, which is 30. Using Pythagoras' formula, we can work out that the height of the triangle comes out to be the square root of 3. So using those properties, again using sine, cos and tan, we can write down each expression in terms of the angle in degrees or the angle in radians. So these are useful properties, the reference triangles. Right, let's try that. Here's our complex number, z equals 1 minus root 3i, and we want to determine the value of z cubed. First thing is we must write it in polar form. We need the value for the magnitude of z. X is 1, y is negative root 3. So subbing those in and following the working, we get that the magnitude of z is 2. To find the angle, inverse tan of y over x. So we have inverse tan of negative root 3, and I'll use the radian form this time, but you could easily write the answer in degrees, which will be 60 degrees. So the angle is negative pi on 3, and that comes from this expression, of course. So putting those 2 bits of information in our expression for z in polar form, this is what we obtain, 2 cis negative pi on 3. We want z cubed, so using de Moivre's theorem, z cubed will be 2 to the power of 3 cis, 3 times negative pi on 3. 2 to the power of 3 is 8, and the 3's cancel in here, and we're left with negative pi. So z cubed is 8 cis negative pi. Writing that in expanded form, 8 cos negative pi plus 8 sine negative pi I. Cos of negative pi is negative 1, and sine of negative pi is 0. And this simplifies to negative 8. Of course, if you wanted to check the answer, and that would be a tedious affair, you would work out the expansion of 3 brackets, 1 minus root 3i to the power of 3, and you should end up with the same answer of negative 8. Okay, let's try an example now where the power is a negative value. So let's suppose here's our complex number, z equals 2 minus 2i, and we want to work out the value of 1 over z to the power of 4. First thing, let's write that as z to the power of negative 4, because we want a power that is not in the denominator, and we'll follow the same steps as the previous example. So the magnitude of z, x will be 2, y will be negative 2. So the magnitude of z will come out to be the square root of 8. The angle will be inverse tan of negative y over x, which is negative 2 over 2, which is inverse tan of negative 1, which is negative pi on 4. So that gives us in polar form that z is the square root of 8 cis negative pi on 4. Now we want z to the power of negative 4, so using our formula, that becomes root 8 to the power of negative 4 cis 4 times negative pi on 4. The 4's cancel, and we have root 8 to the power of negative 4 cis negative pi, like that, in expanded form. And just to do a bit of simplifying, the square root of 8 we can write as 8 to the power of a half. Using our index law, we multiply the powers, so a half times negative 4 is negative 2, there we are. And as previously, cos of negative pi is negative 1 and sine of negative pi is 0. So all of this simplifies to negative 8 to the power of negative 2, and writing that with a positive value, 8 to the power of negative 2 is 1 over 8 squared, which is 64. So the final answer is negative 1 over 64. I hope this brief introduction to de Moivre's theorem has been useful. It is a very convenient method of working out powers of z, but remember that the complex number z must be in polar form to begin with. In the next video, we will look at extending de Moivre's theorem to include a combination of complex numbers. So until then, bye-bye.